Welcome back. Another day, another lesson. I'm going to try to lay this one out pretty simply, but this is going to take some getting used to for everyone, I think. So this is a big topic, linear equations. Most of the equations that we can solve on the first test will be of this form, right? Let's just remember what it means to be a linear equation. So a first order differential equation is linear if it has this form right here, right? So a function of x times a derivative of y plus a function of x times y equals a function of just x, right? And the important thing here is that the y's are to the first power, right? That makes this a linear function. And the stuff out front is just a function of x. Okay, if we divide this equation everywhere by a1, right? Divide everywhere by a1 of x. Then we're going to put this into what's called standard form. Standard form. And that looks like this. dy dx equals some function of x times y. Sorry, dy dx plus some function of x times y equals some function of x. Where p is technically this and q is technically this. But that doesn't really matter. What matters is that this is just a function of x and just a function of x. Now, I know the answer already. I know what to do. But if you've never seen this before, it might look a little strange. The idea is we want to force a product rule, right? Because this side sort of resembles a product rule, right? This is like derivative of the first kind of thing, and this is like hold the first kind of thing. Do we see that? Like if you took the derivative d dx of like x times y, you'd get a term with dy dx times x, plus you'd get a term with just y in it, right? That's the idea. That's the idea. You're going to get, when you take a derivative of a product, you're going to get a dy dx and then a y separated by addition with some function of x floating around. So our thought is, maybe there's some special function of x that I can multiply through by. We're going to wind up calling it mu, right? Mu of x. If I multiply the whole equation through by mu of x, maybe I can force this left-hand side to be a product rule, right? And that's the idea. So what I'm about to do is I'm about to go through all the work of finding what mu is in general, right? So for a general p and q, what does mu of x look like, right? What is this mythical mu of x, right? Now, you're not going to have to do this every time. I'm going to show you the shortcut method. Like halfway through this finding mu of x, there's a way to like jump in and do it the same way every time. And I'll make that clear, and we'll do a bunch of examples. So the idea is, like I said, we're going to force the left-hand side to be a product rule so that we can integrate both sides, right? If we can make this side be equal to the derivative of a product, right? Derivative of some product, right? If we can make the left-hand side be a derivative of some product, then all I need to do to solve is to integrate both sides, and I'll get rid of all the derivatives, right? So the trouble here is that there's a dy dx hanging out front, and that doesn't let me solve for y. But if I were to change this into a product, a derivative of a product, I could just integrate the left-hand side and right-hand sides, and there would be only a y in here, right? That's the motivation. So the solution is we're going to multiply through by this new function, mu of x, which is called the integrating factor, right? So this method of solving linear equations is called, unsurprisingly, the method of the integrating factor. The method of the integrating factor. And the integrating factor is mu, right? So that's what we do. We multiply through the whole equation by mu, right? Multiply through the whole thing by mu. So we get mu of x dy dx plus mu of x p of xy equals mu of x q of x. And it's really important we don't forget this guy on the right hand side, excuse me. we would like in a perfect world this left hand side to be the derivative of this product. Right? In a perfect world, we'd like the left-hand side of 1 to be this derivative of a product. If it was the derivative of this product, then by expanding out this derivative using the product rule, right? Using the product rule, we get first times the derivative of the second plus second times the derivative of the first. So this is equation 1, this is equation 2. We have 1. We have 1, right? We have this. And we want this, right? Just by comparing equation 1 to equation 2, I can see that mu x qx is the same as mu x qx. I can see that mu x dy is the same as mu x dy dx. So that means in order for these two to be equal, I just need mu of x p of x to equal mu prime of x, right? In order for the left-hand side of 1 over here to be the derivative of the product, I need mu x px to be equal to mu prime of x, right? That's my condition. If mu prime of x equals mu x px, then that's good, right? That's good. So that's my condition. That's my condition. Comparing 1 and 2, we see that mu prime of x has to be mu x px. Solving for mu x is what we're after here. So I'm going to divide both sides by mu, right? Divide both sides by mu x. And I get here. And if we remember how we take a derivative of the natural log of a function of x, right? Taking the derivative of the natural log of a function of x gives you 1 over f of x times chain rule, right? Chain rule, f prime of x. And when you know it, that's what this side looks like. These look the same, which means this must equal the derivative of the natural log of mu of x, right? That must be this side. So we get here. Now I just need to integrate both sides, right? Integrate both sides. I get natural log mu equals integral of px. Technically we're supposed to add a plus c, but that's okay. It'll turn out to not matter. And then the last step is to raise both sides to the exponential. That cancels the e in the natural log, and we're left with mu of x equals e to the integral of px dx, where this px is this function here out front of y. The function of x out front of y, right? If I can find that function of x out front of y, and it's an integrable function, I can find the integrating factor, which lets us solve the linear equation. Please, please, please just put this in your memory and commit it to memory, okay? Commit it to memory. Something very important I should have mentioned earlier, but I failed to. In this equation, right, it's super crucial that there's a 1 out front of the dy dx. It's part of the definition, right? If there's not a 1 out front of dy dx, you have to, like if there's a function out front of dy dx, you have to divide everywhere by that function first. Like, I can't just use this equation here and call this my p of x, because this is not a 1, right? This has to be a 1 in order for this to be p of x. right? So make sure when you're doing this method that you have a 1 out front. And then your integrating factor can be found by integrating this p of x and raising e to that power. Once you have mu of x, you can jump back to where we were before, right? This mu of x right here, forces a product rule on the left-hand side, right? This forces a product rule on the left-hand side, which means I can cut to this equation. I can cut to this equation. The derivative with respect to x of mu of x times y is equal to mu of x times q of x. Integrate both sides. Integrate both sides. If you integrate here, dx, and you integrate here, dx, this and this will cancel, and you'll be left with mu of x times y. And then by just dividing both sides by mu, I get y equals this guy. Don't forget your plus c. Don't forget your plus c. And just a quick note here that technically mu of x is supposed to be this e to the integral of p of x dx plus a constant. But since this works for any constant, we're just going to pick c equals 0. But in the final step, we have to have this plus c. So don't forget this one. Do not forget. He's necessary. He's not necessary. Okay. Number 2, it's critical that we put the ODE in standard form. I already said this. I guess I should have waited a second. And that we multiply both sides by the integrating factor, right? Do not forget to multiply the integrating factor to the right-hand side. That's just as important, right? Just as important. Let's do an example. Okay, here we are. Here's our differential equation. dy dx minus 3y equals 6. First of all, is this linear? I'm seeing a dy dx to the first power. I'm seeing a y to the first power. I'm not seeing any other y's multiplied. Excuse me. Oh, Lord. It's late here. I'm not seeing any other y's multiplied. This is a linear function. It's in standard form. How do I know? There's a 1 out front of the dy dx, right? The dy dx is lonely, and it has a coefficient of positive 1. There's no restrictions on px or q of x. So, what do? In order to solve this linear equation, we first need to find the integrating factor. Once we have the integrating factor, we can cut to this point, right? Literally, you just calculate the integrating factor, cut to this point. Find the integrating factor, cut to this point. How do we find the integrating factor? Mu is the integral of, mu is e raised to the integral of px dx. And this right here is px, right? This guy right here is px, and this guy right here is q of x. Right, so since px equals -3, I know, because I did all that work in general, right, we did all of that integrating factor business for a general p. So in this specific example, mu is the integral of -3 dx. E raised to the integral of -3 dx, which is, how do you integrate -3? You get -3x, right? Which is e to the -3x. This is my integrating factor. It's also called the integrating factor because the next step after you find it is to integrate, basically. Right? So again, this step is optional, right? This is an optional step. optional step. I'm going to multiply through my whole equation by mu, right? This is mu. Multiply the whole equation through by mu. Now the left-hand side, automatically I know this is a product, a derivative of a product between mu of x and y. Derivative of the product between mu of x and y. And that's equal to q times mu. Q times mu. How do I get rid of this derivative? I'm just going to integrate both sides. Integrate dx. When I integrate this derivative, they cancel. And I'm left with e to the negative 3x times y. On this side, I'm going to integrate 6e to the negative 3x. How do you integrate e to the negative 3x? Integral of e to the negative 3x is negative 1/3 e to the negative 3x, right? So now I get 6 over negative 3 e to the negative 3x plus my friendly integrating constant. And now all I need to do to solve for y is to divide everywhere by e to the negative 3x. Right? Divide by e to the negative 3x. When I divide by e to the negative 3x, divide by e to the negative 3x, divide by e to the negative 3x, right? These are going to cancel. And exponent rule says 1 over x to the negative nth power is equal to x to the positive nth power in the numerator. So dividing by e to the negative 3x means I can multiply by e to the 3x. Right, this is just exponent rules. And of course, add a solution of integration, an interval of solution, pardon me. And that's it. This is the solution, the family of solutions, all of these solutions to this differential equation. You can find specific solutions by, excuse me, you can find specific solutions by plugging in initial conditions and pinning down C. Let's do another example. X dy dx minus 4y equals x to the 6 e to the x. Okay, is it linear? Is it linear? I'm seeing a function of x times dy dx. No other y's here, right? I'm seeing negative 4y. This is linear, and this over here is just x, so it's also linear with respect to y. This is a linear differential equation. And it's first order, because the highest derivative is 1, right? The highest derivative is 1. So what do I do? What do I do? Well, I need to have it in standard form, right? Need to have this equation in standard form, so I'm going to divide everywhere by x. Divide everywhere by x. And I get dy dx minus 4 over xy equals x to the 5th e to the x. Now in this case, my p of x is equal to negative 4 over x. Negative 4 over x. So how do I find my integrating factor to solve this? Well, I'm just going to raise e to the integral of negative 4 over x. E to the integral of negative 4 over x. That's what I do. E to the integral of negative 4 over x. Now, when you integrate this, the integral of 1 over x is equal to natural log absolute value of x, right? Integral of 1 over x is natural log absolute value x. The negative 4 is a constant. It can just kind of slide out front. And I get mu of x equals e to the negative 4 natural log x, absolute value x. And since, where do we say it? Oh yeah, I didn't mention this before, but we need to have p of x be differentiable and q of x to be differentiable. So since this has a singularity at x equals 0, I have to pick either x is greater than 0 or x is less than 0 for my interval. And I'm just going to choose the positive one, right? So I'm just going to assume that x is bigger than 0. So since that's the case, since I'm assuming x is bigger than 0, I can just forget about the absolute value bars, like they didn't exist. Okay. Now, log rules. Log rules. Again, this class is a lot of pre-algebra, pre-calculus rules that you've probably forgotten about, that get used all the time. So this log rule says if you have a times some logarithm, right, you can take that a and bring it as an exponent on the x, right? Take this a and bring it as an exponent on the x, right? That's what it means. That's what this means. So another thing we need is, in order to cancel a natural log and an e, we need there to be nothing in between the two things, right? In order to cancel the e and the natural log, they have to be right next to each other. There can't be any constant between them. So in order to get there, we just take the 4 and slide it up here as the exponent on x, right? That's what we do here. And now that the e and the natural log are next to each other, I can cancel them, right? So my integrating factor is x to the negative 4th power. X to the negative 4th power. This case happens a lot, right? It happens a lot that you have a constant over x as your p, and after you get to the end, you have x to that constant power, basically is how it works out. Excuse me. Now that I have my integrating factor, I can cut to this point. Integrating factor times y, all taking the derivative of it, right, is equal to integrating factor, right, this is mu, times q, this is q of x from earlier, right? If I look up here, right here, this is q of x, right? Do not forget, when you jump to this step, to add mu on the right-hand side. Add mu on the right-hand side. Okay, so when I combine these together, I'm going to have x e to the x, right, after simplifying this side. Okay, to get rid of the derivative, I'm just going to integrate both sides, right? Take an integral of both sides. The integral and the derivative over here cancel, and I just got to find the integral of the right-hand side. So I've got x to the negative 4th y equals the integral of x e to the x. Now this is the moment where you have to remember how to do integration by parts, right? To do integration by parts, you need a u and you need a dv. And for u, you always pick the thing that you want to reduce the power of, and then dv, you pick the other thing, right? That's the deal. And then when you take a derivative of u, you get 1, and when you integrate v, you get e to the x, right? And in order to do the replacement, right, for the integration by parts, it's u times v minus v du, minus the integral of v du, right? So this right here is the integral of u dv, and I want to set that equal to u times v minus the integral of v du, right? That's integration by parts. Integration by parts. So that's what I do here, right? That's what I do here. U is equal to x, dv is equal to e to the x, du is equal to 1, v is equal to e to the x, which means this equals x e to the x minus the integral of e to the x dx, right? You do this times this minus the integral of the bottom. So I get x to the negative 4th y equals x e to the x minus e to the x plus a constant. Don't forget your friendly constant, right? Remember, it's okay that we drop the constant here, right? Constant of integration is only okay to drop when it's in the when we're finding the integrating factor. But other than that, we need to make sure we add our constant of integration. Constant of integration. Now, last step, divide everywhere by x to the negative fourth, right? Divide by x to the negative fourth, divide by x to the negative fourth, divide the constant by x to the negative fourth. Please don't forget to divide the constant by x to the negative fourth. And we get y equals x to the fifth e to the x minus x to the fourth e to the x plus a constant times x to the fourth. For x in this interval, right? Remember, way up here, I chose this interval. Okay, that's example number 2. Example number 3. A little bit harder. A little bit harder. We've got x squared minus 9 times dy dx equals, plus xy minus x equals 0. This is not in standard form. Is it linear? I'd say yes. This is only x's. This is a y to the first power. This is only x's. This is a y to the first power. And this is only x's. So this is a linear differential equation. But it's not in standard form. In order to put it in standard form, we need to move this x across and divide everywhere by x squared minus 9. And that's exactly what we do, right? That's exactly what we do. dy dx plus whatever this creature is equals whatever this creature is. This is a 1 out front. That makes this p of x. That makes this q of x. And since I'm dividing by something nasty here, right, I need to make sure that I'm only considering p and q where they're integrable, right? These are continuous when, I guess I should say when this is not equal to 0, technically. Right, when x squared minus 9 is not equal to 0. So that's when x is not equal to plus minus 3. Okay. Here's my p of x. In order to find the integrating factor, I have to set e to the integral of p of x dx. And since this is quadratic over linear, I can do a u substitution. Thank goodness, right? Thank goodness I can do a u sub. I'm going to do u equals x squared minus 9. And in that case, du is going to be 2x dx. Right, so I'm actually going to have e to the integral of 1/2 1 over u du. Right, that's my integral. And when I integrate that, I get e to the 1/2 natural log absolute value u. And since u equals x squared minus 9, I get this. Now again, I want to cancel the e in the natural log, but I can't because there's a guy hanging out in the middle. So I'm going to take him and I'm going to stick him as the exponent of x squared minus 9. Right? Slide this guy up here as the exponent of x squared minus 9, and I can cancel the e in the natural log. Boom. Now, if x squared minus 9 is positive, really it should just be, why does it need to be positive? Why does x squared minus 9 need to be positive? I think it just needs to be non-zero. It doesn't particularly matter. Yeah, it doesn't matter here. But now it matters, right? Because I'm taking the square root, so I need this guy to be positive. Right, I need this guy to be positive. So you can either take the -infinity to 3 interval or the 3 to infinity interval. Normally we pick the positive numbers because, I don't know, we're humans and we like the positive numbers, so we just pick that interval oftentimes. Yeah. Okay, so we found mu, right? And we have our equation here in standard form, which means we can jump down to the solution. derivative of mu times y, this is mu, right, equals mu of x times q of x. Mu times q. Integrate both sides. Can cancel this one, right? Integrate this one dx, integrate this one dx. Can cancel these two. And I'm left with square root times y equals the integral of this thing, whatever this is. And again, I can do another, since this is a quadratic over a linear, I can do another, the same exact use of I just did. It's going to change the integral a little bit, but it's not too bad, right? Because now this is integral of 1/2 e to the, integral of 1/2 1 over u to the 1/2, which is integral of 1/2 u to the negative 1/2 power. All right, now how do we integrate a power? We add one and we divide by the new power, right? So this will be u to the 1/2 divided by 1/2, which is multiplying by 2. That's where this comes from. That's where that comes from. So now, and don't forget our friendly constant of integration after this integral. Now all I need to do to solve this is to divide by this square root right here, right? Divide by this square root. This and this cancel. And I get y equals, right? If I, this is x squared minus 9 to the 1/2 power. Let's remember that. If I divide by this here as well, right? These will cancel, these cancel, and I'm left with a 1. And then I've got c over this on either one of these intervals. Doesn't matter. Okay, next one. dy dx plus y equals f of x, y of 0 equals 0. So this is going to help us pin down our constant of integration at the end, right? That's all this is going to do. Everything's going to be the same, except for the very end, we're going to be able to solve for c. Excuse me. But in this case, f of x is going to be some strange piecewise function, right? It's going to be 0 if x is bigger than 1, and 1 if x is between 0 and 1. So if you don't remember how to graph these things, this is what's called a piecewise function, right? And it looks something like this. It's 1 for a while, and then it jumps down here to 0. This is what this function looks like if you were to graph it, right? Okay. Since f is discontinuous, we have to solve this differential equation on this interval and on this interval separately. And we're going to hope that they match up, right? Or we just talk about the solutions on different intervals. So on the first interval, right, on the interval 0, 1, f of x equals 1, right? F of x equals 1. So in that case, my equation becomes dy dx plus y equals 1, right? Dy dx plus y equals 1. Well, in this case, the p of x is really easy, right? It's just a positive 1. Q of x is positive 1. So finding my integrating factor is straightforward. Mu of x is e to the integral of 1 dx, which is just e to the x. Just e to the x. And then I can cut from here to here, right? Derivative of mu times y is equal to mu times q, which in this case, q of x is just the number 1. Integrating both sides, right? Integrate both sides to get rid of the derivative over here. The integral of e to the x is e to the x plus a constant. And when I divide through by e to the x on both sides, right? I get a 1 here, and I get a c e to the negative x here. That's where this comes from. And since I'm on the interval 0, 1, I can use my initial condition, right? Because x equals 0, right? Because x equals 0 is in this interval 0, 1, I can use my initial condition. So pinning down the constant, basically, I plug in 0 for x, 0 for y. I get, if I use this initial condition on this equation, right? I get 0 equals 1 plus c times 0. Nope, 1 plus c times 1. E to the 0 is 1, which means c equals negative 1. That's how we got the minus sign here. All right, so I plug in 0 for y, 0 for x, and I solve for c, and that gives me c equals negative 1. And again, the only reason we can use this initial condition is because we're on the interval 0 to 1. So x equals 0, right, is included in my interval. On the other interval, right, I get dy dx plus y equals 0 because on this interval, if I go back up, f on that interval is 0, right? Again, same integrating factor. It's the integral of 1, which is x, and I raise e to that power, so it's e to the x. The left-hand side becomes a product. The right-hand side, I'm technically multiplying by e to the x here, but since it's 0, it's just all equal to 0. When you integrate the integral of 0 dx, right, you just get c, just the constant of integration. So that means y equals c to the negative, c e to the negative x by dividing by e to the x right here. So we get this solution. This is the solution we get, right? Depending on the values of x, we get different solutions, but we can make them agree, right? We can piece them together. We can choose a constant here that makes these two things glue together to make this a nice continuous function, right? Because a lot of times we just want a continuous solution. If it's not differentiable at a single point, that's okay, but continuous solutions are preferred, for sure. So all we need to do is set these two things equal when x equals 1, right? At x equals 1, set 1 minus e to the negative x. At x equals 1, set 1 minus e to the negative 1 equal to c e to the negative 1. Right? Solving this for c tells me that c better equal e minus 1. So therefore, a continuous solution on the whole interval is this whole thing. Right, where this constant is this guy, which was made so that they agree at x equals 1. Right, we want them to meet up at x equals 1. Okay, thanks for listening. 2.4 coming out tomorrow. Sorry for the late video.